In this video, we're going to review the solutions to exam 2, and these are going to be the main derivative formulas that we use throughout the exam. Let's begin with the first problem. The first problem says that suppose that f of x and g of x are differentiable functions, then find the derivative of f of x times g of x at the input value x equals 2. Once we find our answer, we want to select the correct one from the list. So we notice that the structure of this expression is actually one function times another function. So when we take their derivative, we're actually going to need to use product rule. So product rule is the derivative of the first times the second left alone plus the first times the derivative of the second. Okay, so this is the general form. We were interested to find the derivative of f of x and g of x at 2. So this derivative at x equals 2 could be found by the expression the derivative of f at 2 times the value of g at 2 plus f at 2 times the derivative of g evaluated at 2. Looking at the answers, we see that that is option C. Now let's look at problem 2. As we're reading through problem 2, we want to highlight the idea that it's asking us for the equation of the tangent line for the function y equals ln of x when x is 6. So I might like to immediately, once I've been given the x value and the equation, I'm going to write the point that we're interested in. So it's 6, comma, inputting 6 into this expression, we get the corresponding y value is ln of 6. So this is our point. We know to find the equation of the line, you need a point, the slope, and the point slope formula. These two together, the equation of the tangent line at this graph. In order to find the slope of the point, we need to find the derivative. We know the derivative of natural log is 1 over x. We care about the value of the derivative specifically at x equals 6. So we get the slope of the equation of the tangent line is 1/6. Then we use the point slope formula for a line. We would get this, algebraically solving to get y by itself, and we would find this is our final answer, solve for y. Looking at our answer choices, and we see that D is the correct answer. Now let's look at question 3. For problem 3, we have 5 different statements, and we're supposed to identify whether they're true or false. The first one is if f of x is e to the negative x, then the 51st derivative is negative e to the negative x. So here I recommend we work through the first few derivatives off to the side, see if we can establish a pattern. Okay. We know the derivative of e to the x is e to the x, and then by applying chain rule, the derivative of e to the negative x is e to the negative x times the derivative of the inside, which is negative 1, which would give us negative e to the negative x. Okay. Second derivative, negative e to the negative x times negative 1. Negative times negative is positive, e to the negative x. Take the derivative again, and we get e to the negative x times negative 1. It's negative e to the negative x. Here it seems that it oscillates between negative e to the negative x and positive e to the negative x. We take one final derivative just to verify this, and we would get that the fourth derivative is negative e to the negative x times negative 1, which indeed is e to the negative x. Okay. Now looking at the pattern for the first and the third derivative, it's negative e to the negative x. What these have in common is that they're the odd value derivatives. Notice the second and the fourth is e to the negative x. So based on this pattern, we can see that all odd number derivatives will be equal to what we find here, this one and this one. So we know our answer here is negative e to the negative x. We were asked about the 51st derivative, which is odd, and indeed that's what we were expecting. So we would say this 3 subpart I is true. Okay. Now as we look at our next one, it says the derivative of the function f of x equals ln of 6 is 1 over 6. Now here, remember, ln of 6 is just a number. Okay. The derivative of any number is 0, so we know actually the derivative of x is 0. The reason this is faulty is it was an attempted chain rule, but then you got to remember to multiply by the derivative of the inside. In this case, the inside is 6, derivative of 6 is 0, and that's what would give us the 0. So the original statement is false. Let's look at subpart 3. For subpart 3, we're asked to find the derivative of e to the 5x, so this is an application of chain rule. We know the derivative of e to the x is e to the x, the inside function is 5x, so that would give us e to the 5x times 5. Not what we see represented here, this is false. Okay. Our next question follows power rule, so the derivative of x to the 7 is 7x to the 6, that's true. And for our last question, we see that a function is continuous at x equals a, so if it's continuous, then must it always be differentiable? And here, in this case, the good function to think about is some form of absolute value. Notice this function is continuous everywhere, but we see at a, it's actually not differentiable because we have this corner or cusp. So we'll have to say that this is false. This is not always true. Remember, the order of implication is if it's differentiable, then it's continuous. But this is the reverse of that statement, which can be false. So for our fourth problem, we were told that if h of x is f of x times g of x, and we have values of the table given here for f, g, and their derivatives, then find the derivative of h at 4. So I wrote out the derivative just generally of h of x if it's a product of these functions using product rule. And then I substitute in for the value of 4, and here we just have to make sure we read the table correctly. We see that the value of the derivative at 4 of f is 7. So 7 times g of 4 is 1 plus f of 4 negative 5 times g of 4 6. Okay, 7 plus negative 30, and that should give us negative 23 as our answer. Okay, let's look at now problem 5. The position of a stone that is shot with a slingshot vertically upward with an initial velocity of 5 meters per second from an initial height of 5 meters is given by this formula. And for part A, we're asked to find the ball's velocity. Now we want to remember the relationship that velocity is the derivative of position. We've been given a position function, so we can find velocity by taking its derivative. So that would be the derivative of 15, which is 0, plus the derivative of 5t, 5, minus the derivative of 4.9t squared, which would become negative 9.8t. So our final answer, the velocity equation, is 5 minus 9.8t. Find the velocity at time t equals 7. Here we just need to calculate using our formula. Okay. Let's type this into our calculator, and then we will need to include units as our final answer. The units of distance in this problem is meters, units of time is seconds, so our units are meters per second. Now let's look at subpart C. In subpart C, we're asked approximately how long does it take for the stone to reach its maximum height. Include units of your answer and round to 2 decimal places if necessary. So this is a picture of our original expression. So S of t, the stone is thrown upward from an initial height, reaches some max height, and then comes back down to the ground. Now at this max height, what we could notice is the slope at the max height is the slope of this horizontal line, which is 0. Now we know the slope of the tangent line is equal to the derivative value of the derivative at that point. So if we're finding at the max height, that's equivalent to taking, well, when is the derivative of position, which equals velocity, equal to 0. Another way that you could think about this is imagine as an object is thrown and rises in the air, overall its speed is slowing down until it gets to the max height, it has no speed, and then gravity begins to pull it back down. So we would write down our equation for velocity from above, and specifically we are interested at when 5 minus 9.8 t equals 0. So we're just going to solve this equation to get when t is equal to 0, round if necessary, and we get about 0.51 seconds when you solve this equation for t. What is the maximum height the stone reaches? So we know, filling in this diagram, this is about 0.0, or 0.51. To find the maximum height, that would just be s of 0.51. We have the equation for s of, so we'll just type this into our calculator. S of 0.51 equals, evaluating this in our original formula and then rounding to 2 decimal places, we get about 16.28 meters. For the next problem, we're asked to take the derivative. Once we've taken the derivative, we're told to do not simplify. Looking at this first equation, we're asked to take its derivative. It's going to be just using sum rule, but particularly, I would take time to rewrite this term. Additionally, I would notice that this term is really just a number, e cubed some value. So as I rewrite it here, we would keep this the same, 5e to the x plus e to the 3x plus e cubed. And now 9 over x could be rewritten as 9 times x to the negative 1 plus ln of x and 7 to the x. And if I don't recall this off the top of my head, I would look at the formula sheet from the first page and we see there's a derivative formula for some value, some number to x as an exponent. So let's take these derivatives term by term. We'll get y prime equals 5 times the derivative of e to the x is e to the x, plus the derivative e to the 3x is e, leave the inside the same, times the derivative of the inside, which is 3, plus derivative of a number is 0, plus power rule, negative 9x to the negative 2, plus derivative of ln of x is 1 over x times, plus 7 to the x times ln of 7, minus the derivative of 100 is 0. Okay, it said do not simplify, so we're welcome to just leave our answer like that. So just another thing here, don't forget to rewrite first, especially if there's terms like we saw here that we'd want to rewrite so we can more efficiently apply the derivative rules. Next, we're asked to find this derivative, and we see that it's a product where this is our first term times the second term. So the derivative is going to involve product rule, and within product rule, we're eventually going to have to take the derivative of this term. To take the derivative of this term, we'll have to use chain rule. So we begin by finding with product rule, it's the derivative of the first term, okay, which is 12x, times the second term left alone, okay, plus the first term left alone, times the derivative of the second term. In general, the derivative of ln of x is 1 over x, so by applying chain rule, it's 1 over, leave the inside the same, times the derivative of the inside, derivative of 5x plus 2 is just 5. Since we're asked not to simplify, we can leave our answer just like that. Here, as we look at taking this derivative, we just see it's a nested chain rule. We have the most inner function being 7x squared minus 3x. The function, so the function that this is composed inside of immediately is in sine, okay, of x. And then all of this is composed inside the idea of all of this raised to the fourth. So by applying chain rule, we're going to take the derivative of the outside function, which is something to the fourth. By power rule, we bring down the power. Chain rule says leave everything on the inside the same for now. Subtract 1 from the power, times, and now we're going to be looking at taking the derivative of just this, because this is our inside function. But to take the derivative of this is going to involve chain rule again. So we would have the outside function is sine, so its derivative is cosine, leaving the inside the same, all by chain rule times the derivative of the inside, where now this is the inside. So then we finish by multiplying by its derivative, 14x minus 3, and that's the derivative of j of x. Let's look at our next one. Here, this is going to use quotient rule. So we know it's going to be low, okay, times the derivative of high minus high times the derivative of low all over low squared. For the next one of this problem, we see we're asked to take the derivative of inverse secant of 6x squared. So we have a formula for just inverse secant of x, and we notice that the inside of the function is actually another function itself, so this will also involve chain rule. So let me write down the general derivative formula for inverse secant. From the first page, we get that the general derivative formula for inverse secant of x is 1 over the absolute value of x times the square root of x squared minus 1. And then we'll just need to apply chain rule where the inside function is 6x squared. So we would say z prime of x, the outside function is inverse secant, so it's going to be 1 over, leave the inside the same, so the absolute value of 6x squared times the square root of the inside squared minus 1, and then by chain rule times the derivative of the inside. The inside is 6x squared, so its derivative is 12x. Okay. And since we don't have to simplify, we can just leave our answer like that. Okay. Here we're asked to find the second derivative of the function f of x equals e to the 3x times 2x plus 8. To find the second derivative, we have to first find the first derivative. Let's write that down. By product rule, we would get this as our first derivative, and in this case, since we're going to want to take the second derivative, it might be helpful to just simplify this expression as much as possible. Rewriting like this, we can factor out a common e to the 3x. So after just a bit of algebra, we get the derivative simplifies to this, which we could then again apply product rule to get our second derivative. Taking the derivative again, we get this, distributing and simplifying. Okay. And we could simplify finally the second derivative to be this. Okay. So we'll continue with the remaining questions on exam 2 in the second part of this video.